Here's how to evaluate the area between two curves in VCE methods. What we have here is the area between sine of x and cos of x. Now you can see for some portion that cos of x in this dotted line here is actually above sine, but in this other region here that's represented by A2, the sine is actually above the cos. So what we have to do is split up the area into the sections where one function is above another and then calculate those individual sections respectively. So for A1, we can see that cos is above the sine. So what we do is we minus the sine from the cos. So it has to be cos minus sine because the area between two curves is always the top minus the bottom function. Now the x bounds are just the bounds that the x values that bind that area. So for example, it starts at 0 and then we have to figure out where cos and sine intersect. So what I've done on the side here is just evaluated it quickly. So sine of x is equal to cos of x, divide both sides by cos, you get tan of x is equal to 1. Now tan of x equals to 1 has solutions of pi on 4 and 5 pi on 4. So this is the pi on 4 solution, the first one. This is the 5 pi on 4 solution, the second one. So in the A1's case, it's just from 0 to pi on 4. We just evaluate that integral of cos minus sine. So the integral of cos is positive sine of x. The integral of sine is negative cos of x. So for minusing it, that's going to become a plus. And I just evaluate this from 0 to pi on 4. Okay? So sine of pi on 4, I substitute it in first. So sine of pi on 4, I can just substitute it in and evaluate at the same time. So I get square root of 2 over 2 plus cos of pi on 4 is also square root of 2 over 2. And then minus sine of 0 is 0, cos of 0 is 1. So I end up getting for this one, root 2 on 2 plus root 2 on 2, which becomes just root 2 over 1, and then minus 1. And that's going to be that small area, A1. Now just repeat the same process for A2. The only difference is, well, there's two differences. The first one is I just swapped my functions because now in this region, for A2, the sine is above the cos. And then the x bounds are just slightly different. We start from pi on 4 now, and then we go to 5 pi on 4. Again, that was found through this equation here. Now, if I evaluate this, it's going to be very similar. I just have to take kind of like the negative of this, but I could just evaluate it again anyway. This ends up becoming negative cos. This ends up becoming positive sine. So it actually becomes negative cos of x minus sine of x. Now, there's a lot of negatives in here, and I don't really want to deal with negatives. So one fix that I can do is I can get rid of all the negatives, and I can actually just like swap the bounds as well. So make everything positive inside. So get rid of the negative out there, make this a positive, and then I just swap the bounds here. So just erase that. And I go pi on 4 at the top, and 5 pi on 4 at the bottom. Now, if I want to continue this, so it's a bit low here, but if I want to continue this, what I do is I just substitute in the bounds here, okay? So what I do is I go cos of pi on 4, which is again root 2 on 2, and then plus sine of pi on 4, which is root 2 on 2, and then minus the substitution of 5 pi on 4. So this is a bit more complicated because 5 pi on 4 is kind of a unique value. It's in the third quadrant, which means that the cos is negative and also the sine is negative as well. So what's going to happen here is we're going to have minus root 2 on 2 because it's pi on 4 in the third quadrant, and then minus root 2 on 2 as well. So now we just simplify everything. This becomes root 2 here, and then we have minus negative root 2, so this is becoming plus root 2, so we get 2 root 2 from this one. So I'm just going to write this bigger, so we get root 2 minus 1 from this one, we get 2 root 2 from this one, so our total area, A total, is going to be equal to root 2 minus 1 plus 2 root 2, so we have 3 root 2s minus 1 units squared, and that's your answer for this one.